This lesson is going to be on vector subtraction and then scalar multiplication followed by angle between vectors. We're covering 3 topics this lesson. On vector subtraction, what you need to recall from last lesson is how we added vectors. So if I were to add vector A and B, I'd be joining their tails and heads together. So I'll put vector A there, same direction as and magnitude as the one printed, and if I want to do A plus B, it would be B in that direction, and my final resultant vector would be joining from tail to head in there. So that's A plus B. Now, if I were to introduce a negative B vector, that would be the same magnitude but in the opposite directions. That would be negative B. So if I wanted A plus negative B, then I'd have my original A vector adding negative B there, so opposite direction to positive B. My resultant vector would be down here, A plus negative B. Now that is actually the same as if I took vector A minus vector B. That is the rule for vector subtraction. So if you're given two vectors that are minus, you treat them as if you are going to add the negative of the other vector. Simple. We'll clarify with some of these worked examples. So if I want to get vector R minus vector S, that'll be the same as if I were to join vector R with a negative S vector. So we've got some working out space here. I'm going to say vector R is about 3 boxes wide. I'll put that down first. That's vector R. And then I'm adding a negative S to it. Positive S is diagonally across 3. So negative S would be the same, but in the opposite direction. Now I'm joining again, doing it very strategically from tail to head. That means my final vector, my resultant vector of R minus S is there. Example B as well. I'm going to do S plus a negative T plus a negative R. So my S vector is over there. That's my positive one. I'm going to put that down here. And then I need to add a negative T. So it would be in the upward direction across 2 boxes. That's my negative T, followed by a negative R. So it will be across 3 boxes in the opposite direction. That means my resultant of S minus T minus R is here. S minus T minus R. Simple. You see on your next page, there's another example of a different kind. So I'm just going to whip back quickly to this example of our polygon. See how they gave us BC, then CA, so these 2 letters are the same? It makes it really easy to follow because your last point is your next starting point. B to C, then C to D. Or B to C, then C to A. If we were to rewrite this next section, it would be AB minus a negative BC. Now, it's a negative BC instead of a CB because if you remember, if I have C and B here, CB is in that direction, then that means that BC will be in the opposite direction. And that is the negative version of CB. That will then give you AB plus BC, which is AC. Very convoluted, right? But it saves you drawing the diagram, which can get really confusing. So in the next one, again, AC minus CB, minus a negative CB, minus a negative BD. So I've got CC, BB. That means my final vector will just be from A to B to D, A, D. In the next example, you can do this yourself as well, but I just wanted to remind you of the importance of recognizing what the resultant vector is. So it will be where the two arrowheads meet. That means that, and where, so the resultant vector is t here because that's where the two arrowheads meet, but it's t and not s because t starts at the butt as well. So in R, you can, we'll finish this one first. T will be the result of R plus S. Whereas with the next one, you've got R, and you've got two arrowheads there, but not here. So if you flipped P around, it would make it the resultant vector. It will also mean the head will meet the butt here as well. So we'll flip that around. That means that R will be minus P plus Q. For F, you've got a similar problem. You need to flip G around, and then that'll be minus G plus D plus C. In example 4, we've got the following diagram. Find in terms of R, S, and T, RS. So RS is over here, and we want it in terms of R and S. That R and S is our resultant vector, so if we just flipped R, then it would be a vector diagram. Then similarly for SR, I'll use a different color pen. If I wanted SR, that would be, I'd need to flip S then. R minus S. And then for ST, I'll use another different color, ST. I'll need to flip, that's fine here, flip this one, S. So it'll be minus S plus T. So what I haven't mentioned yet, which I probably should have at the start, is this would be the same as this. Okay, you can swap them around, just like positive and negative numbers. Hopefully that clarifies your understanding of negative vectors. Now we're moving on to scalar multiplication. A scalar, if you remember from the last lesson, is a non-vector quantity. So it only has a magnitude. We only know how large or small it is, but it doesn't have a direction. So it has size, but no direction. Okay, so for example, if I were to multiply vector A by a scalar, I'd just be changing its size and not its direction. So if I wanted to sketch 2A, it would just be double the size of A. Half A would be half the length of A, so same vectors, same direction. You might be starting to see the pattern now. If I want a 3A, that looks about 3 times, so better if you can use a ruler in your notes to keep it more accurate, and that might be 4A. You'll notice that because we've only changed the magnitude, all the vectors are actually parallel. Interesting, right? So if we consider the vectors R and S, we want to construct them geometrically. I think I might leave this example to complete yourselves. You can find the solutions up on the top of this OneNote as a PDF document. Moving on to angles between vectors. I'll give you the definition first, just so you can see where we're trying to head. If I've got a vector, say A, and I've got another vector, say B, I'm going to draw a line between them to form a triangle. I'm going to say that that is theta, the angle between the two vectors. The rule is x squared equals the magnitude of A squared plus the magnitude of B squared minus 2 times the magnitude of A times B x cos theta. That looks familiar, doesn't it? It does kind of look like the cos rule. So let's just go through some of these examples and tease out, prove that formula, see where it comes from. In this example, we've got a rectangle OABC. They've given you two vectors here, A and B. Part A, express the two diagonals in terms of A and B. So diagonal 1 would be, let's try and draw a straighter line, diagonal 1, OB, that would be vector A plus vector B. So if I just picked up B and moved it here, it would make it a perfect vector diagram, closed vector diagram. So you'd have A plus B. Now, if we were to express the other diagonal in that direction, AC would be negative A plus B. So if we flipped it in that direction, if we flip that one, negative A, then it will form a nice vector diagram. Part B, find the magnitude of OB. So remember the notation of the vertical bars meaning just the magnitude, meaning just the length, not the direction. So if I just wanted OB, it would be the hypotenuse of the right angle triangle, with OA being 8 and AB being 6 stated here. Then that triangle will be, that hypotenuse will be 10 because it will be double the triad of 3, 4, 5. So that would be 10 units. Now for the magnitude of OB plus CA. OB plus CA be in that direction. So I've just imagined CA being there and I've just moved it down here so I can create my vector diagram. That would mean that it would be double this double length OA, which is 8 plus 8, which is 16. Now it's asking for OA plus AC plus CO. So you can see it's gone to C, then back to O, which means that the final is a 0 vector. Okay. In example 2, we've actually made a mistake in the question of part A. It should be these two swapped around. So we actually mean find AB plus BC plus DE plus, oops, sorry, made the same mistake again, plus CD plus DE. You can see B to B, C to C, D. It means that my resultant vector is just from A to E. Right? Part B we will leave out and come back to it when we've done a few more things about vectors. Now, going back to what our original intention was to prove this formula, just note we can simply explain it by looking at it in terms of it being a triangle. So if I remove these arrows from the diagram, then I'd only be referring to the magnitude of the vectors, treating them as a length. That means that x squared would be equal to a squared plus b squared minus 2bc cos theta. I've just made a mistake here. That should be a times. So it's synonymous with x squared equals a squared plus b squared minus 2ab cos theta. You can write that out again as well. C squared equals a squared plus b squared minus 2ab cos c, which is probably the one that you see on your formula most often. So you will use this formula when you are completing your exercises stated here. So you've already completed the first 3 from previous lesson. Now your job is complete the next 3. Hopefully this video wasn't too long. I'll see you all in class for you to do those exercises. And if you have any questions, by all means, please ask.